Thank you very much. And I'd first like to start by saying that it's a great pleasure and honor to have the chance to speak here at this 80th birthday conference of Professor Fadeev. So yeah, I really appreciate that. And well, somehow, as you see from the title, there's perhaps a little bit of irony. So far, there was relatively few R matrices, quantum groups, and so on in the talk. So I shall try to sort of fill that gap and present something which is perhaps, well, a continuation of something which is by many, I guess, considered as one of the highlights of what St. Petersburg School has produced under the direction of Professor Fadeev, namely this link between integrable lattice models and quantum groups, and well, ideally, in the end, I dare to predict. I will dare to predict that there's indeed quite a bright future ahead in this direction. So, but to begin with, I want to, well, remind, also partially to set up some notations and sort of to set the stage of well, how one can formulate the basic connection between spin chains and quantum groups in a nutshell. So let me start from spin chains, but of course here I have to be very brief, very schematic, so bear with me. So what are the key players, the key ingredients? Of course there are going to be Lex matrices, so some L of lambda, which is endomorphism or matrix or operator on a tensor product of spaces, say here just generically denoted V tensor W. This is what we would identify as auxiliary space, and this is what we call the quantum space. And R matrices play, of course, very important role. Oops, sorry. That's a little. And one of the key relations I just write in schematic form is, of course, this famous RLL connecting the two. And then the way it goes is that one constructs a spin chain by taking a quantum space which is tensor product of some factors. And so the monodromy would then be formed as a product of local Lex matrices, and it would be, say, endomorphisms of auxiliary space times a tensor product of a collection of quantum spaces. And then there's transfer matrix, maybe I should say matrices, because we have, of course, the freedom to choose V to be whatever we like. That is more a matter of convenience. So then we take trace of M, and this gives us our T of lambda, which is operator on the quantum space, of course. So that is sort of what we need to recall about spin chains. So about quantum groups, before I state the relation. Okay, so what is it? We have Hopf algebra denoted A. Here, of course, there's a certain supply of choices. We can consider, we will be mainly interested in the case where A is quantum affine algebra. Say, for example, SLN hat, for example. Well, Hopf algebra means we have structures delta coproduct as well as product. And maybe I use space. Yeah, maybe here, say, just for, again, introducing notation. In this case, the algebra has generators EI, FI, KI, I equals, say, 0 to some R. And the relations, probably most of you can write by heart, so there's going to be something like EI, well, no, KI, EJ is Q to the AIJ, Aij being Cartan matrix, Ej, Ki, etc., etc. There's a whole list of relations, most complicated being, of course, Serre relations. And let me put up, better read. And of course, we can define the coproduct then by describing its action on the generators. For example, like that, plus all the similar equations that we have to write for Fi and Ki. Okay, so this is how we can define quantum affine SL2N, for example. And of course, main player is universal R matrix. So, which is defined by properties, by the property to conjugate coproduct into opposite coproduct, where tensor factors were exchanged, and we have relations of the form coproduct acting on first tensor factor of R gives R13, R23, for example. And, well, something where delta is here. I shall not write it. Again, most of you will know this by heart, of course. And then consequences Young-Baxter. And, well, what is also well known is, of course, that we can solve this condition by assuming that R is, in fact, in tensor product of Borel halves, where this is what is generated by, say, EI Ki, and this would be generated by Fi Ki. And then it will be of the form Q to the T R bar, where R bar can be written as 1 plus some, maybe with some coefficients, EI Fi. Again, I'm very schematic here. So where these are certain monomials, maybe I should, of course, write here EI Fj, monomials in Fi, etc. So that's the general form. And yeah, so what's the connection between spin chains and quantum groups? So this can be put into the following very concise and nice statement. There exist representations pi lambda v, pi lambda w, such that the L of lambda is, say, pi lambda v tensor, say, pi, maybe 1 here, w on R, and the R of lambda over mu is pi lambda v tensor pi mu w on R. So here is a quantum group spin chain connection in one statement, namely everything comes from universal R. That's sort of the main, very beautiful statement that was ultimately. What's it? Here? V, yes, thank you. Sure. Right, and this is, of course, extremely powerful and, say, also for practical purposes, because then, for example, playing with V and playing with a representation theory of quantum affine algebra, one can derive functional relations for the eigenvalues of the transfer matrix and its higher generalizations, and solving this is the practical tool for studying the spectrum. So all these relations, they have a representation theoretic origin. But of course, you have to also to be careful about really what W exactly is to figure out the analytic properties, and this then defines a closed problem from which you can actually calculate the spectrum exactly in many cases. So this link really is of great practical value, even for, say, the sake of calculations and so on. Good. So this was sort of the lightning review of quantum group spin chain connection. So the main part here is going to be now, and maybe this is present, or let me also put question mark here. It's about discretization of integrable quantum field theory. So this is my main interest in the subject, at least. So regularization of integrable Q of t in 2 dimensions, of course, but maybe there's a way to go beyond. And for this, basically, we want to use something that has been proposed by Faddeev and Volkov, which you can see as a useful variant of the spin chain, which is the light cone lattice. Well, I cannot write very well, but so somehow, of course, again, in a nutshell, the main idea is to factorize the Lax matrix, which we use to define a spin chain, as product of 2 factors, which we think of describing, say, infinitesimal parallel transport along light-like segments, so that we deform, say, the contour along we integrate to define monodromy matrix into a saw-like chain, and then, say, to each saw here, we would associate either L plus or L minus matrix. And accordingly, of course, we have a splitting of the space W as, say, tensor product of 2 spaces, etc. I don't have much time to talk about this in great detail, but okay, maybe I move this up. But one of the nicest observations that were made in the investigation of this light cone lattice approach by Faddeev and Volkov, and then there was subsequent work which uses the formulation I shall give here by Bajanov, Bobenko, and Reshetikin. So this is about the integrable, how to introduce an integrable evolution on a light cone lattice. And the observation is all we need to construct such an evolution is again some R matrix. Here we introduce labels which are labeling sides on this chain. So it will be something like the minus here comes with a 2n and the plus would come with 2n minus 1, etc. And so this is a sort of leg numbering notation we're using here. Minus 2n lambda plus 2n minus 1 mu, and again multiplied with a r from the right, 2n minus 1 comma mu. Does the usual thing, it just swaps the places, 2n minus 1 plus of mu minus 2n of lambda. So if we have such an R matrix which does this job, then we can immediately write down time evolution operator whose evolution is going to be integrable basically automatically thanks to this equation. U plus minus, that's for the evolution in positive or negative spatial light cone directions. And then there's the product over these factors 2n to n minus 1. And we have here, say, mu and mu bar. Let me not comment on all the details here because I really don't have the time to do that. But so here, what you see, the mu bar will contain some parameter like the mass parameter of the model. That's how it's introduced here. And then there's some simple shift operator, C odd or even to the plus or minus 1, which is simply defined by properties like C odd, for example, on some observable at place 2n minus 1. It will shift by one physical lattice side like that, and it does nothing on the even sides and vice versa. I think that should be clear then. So this is a variant of the spin chain that you can use to discretize models such as Sinch-Gordon and then later work by Kashav and Reshetykhin, they generalized this to affine toda, which is in fact the class of models where we, in the work with Carlo Meneghelli, my collaborator from Hamburg, a postdoc, we want to go further. And right. So this is basically spin chain side. How about quantum group side? Well, according to the ideology I started from in the very beginning, we should write down representations such that the correct Lex operator and R operator come from these representations. So let's write it. So here UQ SLN hat. Okay, so first of all, basically for auxiliary space, we have a representation we call pi f. F is for fundamental, sometimes called fundamental evaluation representation. Well, these are formulae that most of you will also know very well. Here we have, well, I had previously Ki, now I use Hi such that Ki is Q to the Hi, okay? That's not so interesting probably. The other thing is perhaps a little more interesting, although simple, still very simple. So to introduce the next representation we will need some sort of Weyl algebra defined by these commutation relations. Sorry, j plus 1, I suppose. Let's check. Yes, of course, j plus 1, vj ui. And then here, so okay, for the moment, we can leave open what the representation of this Weyl algebra is going to be. We just write something in terms of this Weyl algebra. Pi lambda plus of ki would be ui plus 1 to minus 1. And then there's the representation pi minus. This I called kappa, so I want to also call this here kappa. EI. Well, note this representation is representation only of a Borel half, but I told you that the R is in the tensor product of Borel half, so that's going to be good enough for us. An observation which was very much stressed by Bazhanov, Lukyanov, Zamolodchikov, but of course it was probably very well known in this community. So here we have, we introduce a bar to denote a second family of oscillators. Oh, there was a -1 here, I forgot to write. Bar, and this is basically just the same up to sine perhaps. Yes, there is a u bar to the -1 plus 1 bar. And here we wanted to use kappa. Good. So this defines three representations, pi f, pi plus, pi minus, where these are representation of Borel minus, Borel plus, respectively. Well, and then the statement is, and this was essentially already observed in slightly, but not essentially different form by Kashav and Reshetykhin. There's an L plus, and here there's something very interesting I may return to a little later about proportionality. Namely, in this formula we have to drop a factor, which strictly speaking here, in fact, will be infinite a priori, in order to get something reasonable. So for the moment, let me be imprecise, but I hope to have time to comment on this a little later again pi minus kappa on r minus. What is r minus? In fact, there is of course certain symmetry in the definition of universal R, namely along with a universal R as defined, there comes a partner where B plus and B minus are swapped. So we can introduce an R minus just by this relation, and R plus is just a new name for what we previously called R. So it is just, we take the inverse and swap the tensor factors, and we get a second guy where roles of Borel halves were swapped. Well, and the statement is, these are really what are sort of the most honest possible Lex matrices for discretization of affine toda. Namely, if you just follow straightforwardly sort of the discretization strategy by introducing averages over, say, segments along some initial value contour, that's what you would find. That's the statement that is, of course, well, I mean, takes a little bit of work to verify, but it is true. So this is for discrete affine toda. So this is how these Lex matrices come from the universal R. And let me, well, just squeeze into the corner here. Then the relationship, what we have to specify is, for example, so then we have an index n for some side again. So this variable, for example, will be related to the affine toda field phi I. So it has fields according to the simple roots in the SLN, for the SLN Lie algebra. And it will simply be the exponential of this field at some integer multiples of the lattice spacing delta. So this is lattice spacing. And then there are similar formula for the U's. They are basically exponentials of derivatives of this field phi. Do I need more space? And in fact, I mean, perhaps the nicest way to see the relation with really affine toda is then to figure out, to just calculate the time evolution which is generated from these operators. So we have defined our Lex matrices. We find some R by solving this relation, which does this job. We form an evolution operator. Evolution is automatically integrable. And we calculate what it gives, and you find a beautiful discrete version of affine toda equations. In fact, also this was in the paper of Kashav and Reshetikin already. So now's maybe time to start with something new. So a first remark I want to make is that in this form, I mean, this type of formalism, in some other work, together with a postdoc, David Readout. So it seems to apply really to very large classes of interesting two-dimensional quantum field theories. And to say what really makes the story much more interesting is if we replace our quantum group by super quantum groups or super affine deformed super affine Lie algebras. And if you do this, then you get indeed, well, not just affine toda, which is already very interesting, containing Liouville theory and generalizations, but if you allow super affine quantum groups, then you find interesting models such as, for example, if you have underlying Lie algebra, or maybe the G hat, to be SL2/2, it would give in just the same way n equals to 2 Susie sine Gordon, which is a very interesting model in its own right because it sort of combines in it sine Gordon as well as sinh Gordon. So it has these non-compact as well as these compact features at the same time. And furthermore, it's known to be dual to a sigma model. So this is an interesting model for if you want to understand, say, nonlinear sigma models as well. Then you could start, for example, from this one. And one observation I want to add to this story, which, I mean, please correct me. I suspect I may be wrong in what I want to say, but I have not found this observation, at least in the written literature I know of. So what we should keep in mind is simply, do I have it still? Yes, it is still here on the blackboard. So if we can get the Lex matrices defining the light cone lattice in this way, then there's basically an obvious way to solve the defining equation for the R matrix that we need to get time evolution. And this is the following. Pi minus lambda tensor pi plus mu acting on the universal R. That's as simple as that and as straight as that. So basically, using this observation, you just take your favorite quantum or quantum affine or quantum superaffine algebra. You build this object, you build these objects, and you get a time evolution from this formula. So in particular, for example, in this way, I mean, there are known, existence of universal R is known for algebras of this type. So they can be treated in much the same way. And so let me refer to this equation as a little r, capital R, just for future reference. And this is the universal solution to, did I give it a name? I wanted to give this equation some name. I call it little RLL. So then this would be universal solution to this equation RLL. And okay, I said it in words. So the conclusion here, there exists basically a universal definition for time evolution. So yeah, I mean, I really like this observation because it says it's a beautiful harmony between quantum affine representation theory with Borel plus, Borel minus, and light cone plus, light cone minus. So they nicely interact with each other in this way. But maybe it was known actually. So yes.
This kind of formula does not always work, yes, because for example, for Q oscillators, so if you take so that this front and the product of T minus plus P by T plus is not decomposable.
Thank you. Yes, of course, this is very formal at this point, and the rest of the talk is exactly about how to make sense of such a formula for representations of our interest. Because well, there are many possible issues. Perhaps the most immediate and pressing is the representations we're going to be interested in ultimately will use the representation of these Wall algebra, which are infinite dimensional. So as R was defined as some infinite formal sum over the generators, probably it doesn't make any sense at all at this stage. So it's exactly the point that I now want to discuss. So maybe here I put with a big exclamation mark, formal, for the moment, purely formal. Good, so let me put it here on the board. The representations of our interest are infinite dimensional in general. And why is this so? Let me be very brief on this. The point is, well, we still have it down here. We had seen, physics tells us, the discretization tells us that the VI variables are exponentials of a real field. So these should be positive variables. This, I think, is hard to get around if this is really sort of what we want to describe. And then we're asking for, and similarly, of course, the UI. So then we have to ask, what representations do there exist of these commutation relations with positive operators? There are not so many. And these are, in fact, automatically of modular double type. So let me put it here like this. First of all, the physics tells us that UI and VI have to be positive. This is very important. And this restricts the type of representation we want to choose, of course, severely. And what this implies is relevant representations are of modular double type. Why is that? Well, there is a simple but also sort of profound link between positivity and this modular duality that Professor Fadeev had observed. So if, for example, our Q is parameterized in terms of parameter B like that, and we can then represent, for example, our UI. Let's just take 1. So just here n equals 2. Then we just need one of these guys. So UI, U is. No. Sorry, I don't have to do this. Just here, what I wanted to say is, I can define UI twiddle as UI to the 1 over B squared. VI twiddle as VI to 1 over B squared. Taking non-integer powers here is, of course, allowed thanks to positivity. So here positivity is used. And then we can show that these generate a dual Wall algebra of this type with a Q twiddle delta ij minus delta ij plus 1. We twiddle I, ui twiddle, where Q twiddle is just e to the minus pi I over b squared. So basically the point about modular duality is if you have one such algebra and if you have positivity, you get the second one for free. Yeah, but our problem is if we have infinite dimensional representation, then what's the meaning of right-hand side of our magic formula relating the little r giving time evolution to the universal r? Okay, so no, with positivity you don't have finite dimensional representations. If you want, for example, you could also have unitary representations, and they can well be finite dimensional. But that's not what physics tells us to do in this case. Good. So how much of time have I left just for?
5 minutes.
5 minutes, so that's not too much, but okay, let me see what I can do. What then? Yeah. Okay. Hard work. Good. So what do I want to use to analyze this issue? There is a beautiful formula for universal R, which turns out to be basically tailor-made for this issue, which is Koroshkin-Tolstoy product formula. Now the question is a little bit how much I should say about this, because I cannot really write it down in this short time anyway, so I shall try to give you just some impression. So what we have to do is choose ordering in the system of positive roots. We have to define root generators, and here I need a little bit of notation. So E gamma, F gamma is notation if gamma is in delta plus over delta plus I should put it downstairs, delta plus imaginary. So there are of course the imaginary roots, and for the imaginary roots we use notation EMI or FM. So M delta, so multiples of the basic imaginary root, and I is some index which runs from 1 to R for the cartan of the underlying finite dimensional Lie algebra, and M is an integer. And there's a recursive procedure to construct them out of EIFI in a recursive way. Well, let me not write any of this. So then what's the form? R is, well, there's cartan part, simple enough. R bigger than delta, this is now just symbols, smaller delta. Where R bigger delta, R smaller delta, this is product, ordered product according to the chosen ordering in the root system over factors given by quantum exponential of simply E gamma tensor F gamma. This is simple enough. So we just take quantum exponential of these basic root generators. And what is sort of the most tricky and least trivial part is about imaginary roots. This doesn't quite work. So, is there questions or yes? How about? This is ordinary exponent of some infinite sum. Well, maybe I should not write it down. Some m and so on. Good.
Minus 1 squared, no?
This where squared here?
Yeah, well, this no, not here. Well, q minus 2 minus 1 squared, isn't it?
This depends a little bit on your conventions, because sometimes this factor q minus q to the minus 1 is absorbed into the definition of quantum dialogism. It depends on what is the exact. So the convention I was using, this would be correct. Yeah, there's a little bit of issue with this. So here we have then the EM delta I tensor FM delta J, IJ, M, and so on with some coefficients. Good, so maybe, well, this I claim is tailor-made for making sense. Can I have 2 minutes? 1. Okay.
Okay. Because this is the last talk today, 10 years, 2 minutes.
Okay, thank you very much. So, what are the key observations we can use to make sense out of this? First, for the representations we're using, the product automatically becomes finite because the higher root generators truncate automatically to a finite number. Product becomes finite. Second point, this is defined by an infinite sum. It doesn't make sense in our context as well. However, of course, we know very well in the context of modular double. So there we're going to have, it turns out, E gamma, F gamma, again positive. So we know what to do. We replace this guy by a non-compact quantum dilogarithm, and then we can check that this sort of renormalization procedure preserves all the good properties that we need thanks to the functional relations that this special function has. And last but not least, and this is unfortunately what please ask me if you're interested, because there's a very interesting story about imaginary root contributions. So how to make sense of this infinite sum here? Well, we have results. So for example, for the representations that we're interested in, these guys turn out to be central, and basically replacing this by some non-compact quantum dilogarithm will also do the job. However, that it does the job is quite non-trivial. So for example, one really needs to check that key properties, like in particular the delta tensor 1 on R, R13, R23, so that this, upon taking representations, is preserved by the renormalization. And for this we have, I would say, fairly non-trivial evidence that it works for our case. So, yeah, I have to stop. The punchline is what I wanted to say is that really, if you bring together some of, I think, what Professor Fadeev's favorite ideas was, light cone lattice, quantum affine algebras, modular double, if you bring this all together, then I think it has a bright future because it will lead to some universal scheme for putting large classes of integral quantum field theories on a lattice. Thank you very much.
Thank you.
Well, maybe let me say some nostalgic. Well, with Sasha, we have written this thing for SL2 case, which is really of Lattice, and well, immediately we have seen that this exponent, the Q exponent, doesn't make sense for Q modulo 1, which must be for Sasha case, and so on. And nevertheless, we have published a paper, and then we got a letter, not a letter, but somehow news from Baxter. He says it doesn't exist, and so on. And then I was to do something, and I was in the 90s. I used to visit Finland very often, so I was in training and decided to solve the equation, not to use it as an exponent, but to solve this equation, and then have the ratio of these two exponents. And so Zagier later told me that he was very amazed that there's a function which has singularities for all rational points. And you divide it by another one with also the singularities on all rational points, that the singularities cancel. Yeah. So that was quite invigorating.
This is the magic renormalization. Basically, the other exponent by which you divide is really it cancels one by one all the singularities that for Q at the unit circle the usual quantum dilogarithm develops.
That was the,
so yes.
As I say, it was end of 90s, and I liked it.
More questions? No more questions. Let's thank the speaker again.
Okay, thank you.